Hello, my name is Peter Snyder. I'm from Brave Software, and today I'll be presenting the paper, Who Filters the Filters? Understanding the Growth, Usefulness, and Efficiency of Crowdsourced Ad Blocking. This is work done along with Anton Bastille and Ben Lifshitz. So, starting. First, an overview of this talk. Um, Many privacy tools right now use filter lists, and these filter lists are predominantly crowdsourced. So I've listed some examples here: AdBlock Plus, uBlock Origin, the Brave browser, many others all use crowdsourced filtered lists. Um, However, despite how popular these tools are, how they're maintained and how they are applied to the web is poorly understood. It's not clear who makes the decisions on how what rules go in, how long those rules last, etc. Um, and so in this work, we'll be trying to understand how crowdsourced filter lists work through the lens of EasyList, which is the most popular filter list. So an overview of what I'll talk about. First, I'll talk about EasyList and some background or context about how EasyList is maintained. Then I'll talk about the methodology of the experiment we ran in this work. Then I'll talk about some of the results we found. Then I'll talk about some ways that we were able to apply those results to improve filter list application for users. And then I'll conclude with some discussion. So first, some background. So as I mentioned, EasyList is the most popular filter list right now, although there's many others. EasyList predominantly targets ads. This is distinct from other filter lists like Easy Privacy, which targets primarily trackers, or filter lists maintained by projects like uBlock Origin that target other resources on the web. EasyList is a text document, and it's made up of new line separated rules that are all in a regular expression-like format that describe URLs or page elements. EasyList is a very large project. It's been around for 15 years and comprises many tens of thousands of rules. EasyList is predominantly an English site, and so it targets the global web. I say global in quotation marks because really what it means is the English web. They're language-specific variants of EasyList that target different linguistic areas of the web. And then last, EasyList is made up of many different types of rules that all target different types of resources at different levels of the web stack, and I'll go into more detail about that in a bit. So as I mentioned, EasyList contains several different types of rules. It contains network rules. Network rules describe web requests that should be canceled. So in this example, this rule would say don't load resources that match the path add from the origin example.org. EasyList also includes element rules. Element rules describe elements on the page or subtrees in the DOM that should be hidden. So this rule here would hide all iframe elements on the site.com. EasyList also includes exception rules. Exception rules cancel out other rules, and so they say don't apply to any other rules in this case to advance on example.org. And then last, rules can be decorated with different filters, which say only block scripts in this example, or if this rule only applies to third-party resources, things like that. A little history about EasyList. So EasyList was started back in 2005 as an individual project. In 2009, it moved to GitHub and started building up a significant number of contributors. In 2013, it had an enormous or significant growth when it merged with another popular list called Fanboys List. In 2019, which is when this study concluded, it contained 72,000 rules. As I'm speaking right now, it contains about 69,000 rules, and some of the shrinking or some of that reduction is a result of this study. So now I'll talk a little bit about the life cycle, or how long rules stay in EasyList. So according to our measurements, the average rule in EasyList, or about 50% of the rules in EasyList have been there for over 4 years. And so there's not a lot of pulling rules in and pulling rules out. For the most part, when a rule stays in, it stays in for a long time. And then last, just to conclude this background section, we measured or explored who contributes to EasyList. And so people who want to contribute to EasyList can do so in primarily two ways. One is they can communicate on the forum for EasyList, where people discuss new rules that should be added. And then second, people can contribute directly through the repo in GitHub by filing issues and discussing there. Despite the popularity and size of the project and how many people rely on it, there's predominantly just 5 people who maintain the project. Or over 3/4 of all commits to the project are made by just 5 different authors, though there's a significant long tail of people who have made a smaller number of commits to the project. Last, there's a number of other measurements in the paper, or topics in the paper in the background section that I just want to mention here, though I won't go into details. So that's some details about how we measured the history of the project across its reorganizations and the tools we used for understanding EasyList and things like that. Those are all details provided in the paper. So that's a little bit about the background of EasyList, or how EasyList fits into the content filtering world in general. Now I'll talk a little bit about the methodology for the study in this paper. So before I talk about the methodology, I want to talk about the goals or what we're trying to solve or what we're trying to understand. So the broad goal is to understand how EasyList interacts with the web, or if you're using EasyList, how it modifies your browsing experience. But under this broader goal, there's several sub-goals. One is we want to understand how useful the different rules in EasyList are. So are all rules equally useful, or is there some skewed distribution? Next, we want to also understand if there's some relationship between how long a rule has been in the list and how useful it is. Are newer or older rules more or less useful? And then last, we want to see if we can understand how advertisers respond to being blocked by rules in EasyList. So our methodology for doing so was pretty straightforward. First, we instrumented a browser. Then we selected a set of websites that we thought were representative of typical browsing behaviors. And then last, we applied EasyList to the resulting crawl data to understand what got blocked and what didn't. And now I'll step through each of these in turn. So first, as I mentioned, we instrumented a browser. We used the current stable version of Chromium at the time. And then we automated that browser with Puppeteer, which is a library for using the DevTools protocol to automate the browser and to also get some understanding of what the browser is doing and the types of resources it's fetching. And so we instrumented the browser to record all URLs that were fetched, along with the responses to those requests, the contents of the requests, things like that. I want to highlight that this instrumentation didn't modify in any way how the browser behaved. So this is all passive instrumentation, and so would be invisible to the page. And the last, for reasons I'll go into in a little bit later, we didn't measure how element rules applied to the page. So all the measurements we took are just at the network layer, and I'll explain why we made that choice a little bit later. But I wanted to highlight it here in the instrumentation section. So once we instrumented the browser, we need to figure out what web pages to set it on and how to understand the web in general, how to build a representative crawl. And so to do so, we selected 10,000 domains. These 10,000 domains were the first of the 5,000 most popular sites in the Alexa popularity rankings. And then also we selected another 5,000 origins from Alexa to represent unpopular sites. So we selected 5,000 sites randomly from Alexa ranks 5,001 to 1 million. And so we have a popular list, 1 through 5,000, and an unpopular list, 5,000 sites that are between 5,000 and 1 million. Then once we had these 10,000 origins, we measured the landing page for each of them, and then we selected three child pages on the same site. I'll go into a little bit more detail about that in the next slides. And then we repeated this measurement every day for 74 days. So we had a longitudinal measurement. And then for each page we measured to, we also measured for 30 seconds. So we allowed the page to load for 30 seconds and recorded the resources that were loaded during that time. And then again, I just want to highlight that this was a passive measurement. We didn't modify how the page executed in any way. So to see how this crawl worked at a very high level, take CNN as an example. So we set our crawler at cnn.com. In this example, we let it load for 30 seconds. At the end of 30 seconds, we extracted all the links on the page. We then removed any links that weren't to cnn.com or ETLD+1 equivalent sites. And then we selected a maximum of 3 of those remaining URLs. And then we visited each of those child pages for 30 seconds as well. So we had a maximum of 4 page recordings for each selected origin. So once we selected our pages, we need to understand both what resources were fetched during the page's loading and also how EasyList affected that. So say we were loading cnn.com, we would note all the resources that were loaded on cnn.com. So here's some images, an advertisement from DoubleClick, a JavaScript file, things like this. And then after the crawl was over, so once we had just the recording of what resources were loaded, we applied EasyList to those and noted what EasyList rules matched, and if so, what resources they were matching. So here, the add rule would block the add image, and the double-click blocking EasyList rule would block double-click. The other resources would not be blocked. Finally, I want to discuss a little bit why we omitted element rules from the study. We didn't do so for several reasons. One is because the primary interest we had in the study was to understand the privacy and performance implications of EasyList. And element hiding rules wouldn't affect either of these. In modern browsers, even hidden elements are still loaded, although sometimes with a lower priority. So the same resources get loaded even if you're hiding some elements, which made element rules not relevant to privacy performance measurements. Second, element rules end up being very highly variable because as you interact with the page or while animations trigger, things like that, different element rules will trigger, adding a lot of noise to the resulting measurements. And then finally, there's a lot of EasyList deployments that don't consider element rules at all. So these are things like privacy-preserving proxies, things like that only consider the network rules. So for these reasons, we only considered the network rules part of EasyList. We did not consider element rules. So in summary, we instrumented Chromium, we visited 10,000 sites, 5,000 popular and 5,000 unpopular, and for each of those sites, we recorded the domains visited, the subpages that we visited on each domain, the resources that were requested, and the EasyList rules that matched. So that's the methodology. Now I'll discuss a little bit about the results that came out of applying this methodology to the web. So we conducted the study between July 24th and October 5th in 2018. Of the 10,000 domains we crawled, 400 never replied once. This might be because of anti-bot technology or just churn in the Alexa list or unpopular sites coming offline, things like that. And then we weren't able to capture 4 pages on each domain, and we attributed this to a number of different things. Some sites just probably only have 1 page. Some sites our bot triggered captchas, things like that. So we weren't able to find 4 pages on every domain, but on average we had 3.74 pages recorded per domain. Next, we measured how many EasyList rules were used. So what percentage of all of EasyList was actually useful when we were crawling the web. And we found that the vast majority of EasyList was never used at any point during the crawl. So during none of the days that we measured on none of the domains and on none of the sites, a full 90% of the rules in EasyList were never used a single time. And to make matters more interesting, only about 5% of rules were used 100 times or more. So there's a very high skew in how often or how useful each rule is. Next, we want to see if there's a relationship between how old a rule is and how useful it is. And so we're trying to answer here, are newer rules more useful? And the answer ends up being a little bit mixed, but mostly no. And the reason here being, during our study, there were 2,000 rules that were added to EasyList during the 74 days of the study. Of these, about 10% or 9.5% of the 2,000 rules were used once, which is roughly similar to the number of pre-existing rules in EasyList that were used at least once during the study. So about 10% of rules that existed before the study were triggered at least once during the experiment. So that makes them seem like old rules and new rules are roughly equal. However, if we dig in a little bit more and we consider we ask, of all the rules that were used at least once, how often were they used? We see that there's a large difference. New rules were used far less frequently than old rules. So new rules were used less than 1 time per day in the experiment, while old rules were used over 6 times a day, conditioned on them being used at least once. So we conclude by this that most of the blocking power or usefulness is already captured by old rules, and there's a declining marginal utility of new rules being added to the list. Next, we want to understand how do advertisers respond to being added to EasyList. And so here, the way we measure this is we look for instances where the same resource was being loaded from multiple URLs, but was only blocked in some cases. And then we compared the URLs of the blocking of the resources requests that were blocked to the ones that were not. So to clarify this, let me step through this methodology in a little bit more detail. So at time 0, say we found a bunch of resources that were blocked by an EasyList rule. So in this case, at the beginning of the experiment, these resources were not blocked. Then during the experiment, some new rule was added that would block them. And then even later in the experiment, we noticed the exact same resources coming from new URLs. So these are compared by hash, not by URL. And then we want to compare what is the relationship between the URLs where the resource was blocked and the URLs where the resource was not blocked. And we taxonomize these differences. So we found 4 different types of advertiser reaction. So the simplest one was changing the domain. So advertisers who wanted to get around EasyList would just move their resources from a domain that was blocked, say tracker.com, to a domain that was not blocked, say benign.com, and that would get them around the filter list. Another possibility was a subset of this, just to move it from whatever domain where it was being blocked to the first party. So instead of changing between third parties, it would move from a third party to the first party. A third case was to remove certain distinguishing ad keywords from a URL. So if a URL had the word ad in it, for example, the advertiser might just replace that with images or something less identifying. And then the fourth type of reaction we saw was many ads have dimensions in the URLs, so 320 by 240 or something indicating how the ad should be displayed. And some advertisers escaped or evaded the filter list by just removing those dimensions. And when we then quantified how often each of these 4 different evasion strategies happened, we find that by far the most common one was just to move to another domain. And of this, the most common domain moved to were CDNs or other domains with shared trust. Finally, there's a couple of other measurements in the paper that I won't go into here, but I just want to highlight. We also do some measurements of how often or how long it takes for advertisers to respond. We give specific examples of organizations who are evading filter lists, things like that. Those are all in the paper as well. Next, I'll very quickly describe some ways that we were able to take these results and turn them into improvements to applications or ways to improve content blocking on the web. In the paper, we described 2 different ways that our findings could be used to improve content blocking. I'll just go into one of them here, but I want to highlight them both. I'll talk about the first one in more detail, and then I'll give a brief pointer to the second one. So the first way we're able to apply our findings to improve content blocking is to take the problem of content blocking on mobile devices. On iOS, for example, the platform limits the number of rules you can apply to 50,000, which is a problem because EasyList itself has 70,000 rules in it. Not only is there a numeric limit, but also there's a performance limit. The first time you load the rules, you have to compile them into a binary format on the device, and this can be very slow and an unpleasant experience for users. It's also a problem because oftentimes EasyList isn't the only filter list users want to use. They also want to use Easy Privacy or some list that's specific to the language they speak, things like that. So this 50,000 rule cap ends up being a significant problem. And the solution we find is to shrink down instead of shipping the entire EasyList, we can just ship only the rules that are very likely to be useful, only load those, and then not only have we gotten below the 50,000 rule cap, but we've also have a much more pleasant compiling experience. We call this reduced list slim list. And just to very quickly show what these numbers look like, this is how long it takes to compile the full set of rules of different filter list sizes on different iOS devices. You can see here at the far right side of the graph that it takes a full 12 seconds on an iPhone 6, for example, to compile just 40,000 rules. But if we extract that down to just the rules that are most likely to be useful, so the about 5,000 rules that are actually used from EasyList in our experiment, it takes about 2 seconds. So it's a much more pleasant experience. Also in the paper, we briefly discuss ways that desktop browser extensions could be modified to take advantage of our findings. And so I leave that for the paper. Finally, I want to conclude with some discussion of limitations and some concluding thoughts. So I want to highlight a couple of limitations or areas for future work in this area. One is that key to this work is the idea that the websites we select are generalized well to people's browsing experiences. So we assume, because our experiment doesn't interact with websites in any way, we're implicitly assuming that interactivity isn't vital for understanding how EasyList is applied to the web. Excuse me. And we also assume that pages that are easily gotten to by the landing pages of domains are very similar or roughly similar to pages that are more deeply nested in the site structure. If either of these 2 assumptions aren't correct, then that would have some bearing on how generalizable our findings are. Second, we assume that our crawl location and the sites that we chose to crawl are similar to the domains or the origins that people crawl. So we assume that measuring from a US IP will be similar to the types of experiences you get if you measure from other IPs. And maybe more significantly, we assume that applying the English the English version of EasyList to the English Alexa sites will give a good generalization for how EasyList works in general. And this may or may not be true. There's some evidence that suggests that actually EasyList isn't as nicely partitioned as the project maintains, and so there's not a clean division between English sites and, say, Spanish sites, something like that. So there's room for future work in understanding how whether, say, Spanish sites are equally as applicable to Spanish EasyList as English sites are to English EasyList. And then finally, we implicitly assume that blocking all resource blocking is roughly equal in importance. So in this work, we've measured how often rules trigger, and we assume that rule 1 or rule X triggering once is as valuable as rule B triggering once, something like that. But this may not be the case. It may be that even if certain rules only are useful or trigger rarely, that it's really important for those rules to work or to be in place for security reasons or other more vital reasons. So there's more work to be done in understanding not just how often different rules are used, but how important different rules are. And so I just want to conclude here. Thank you very much for your time and for your attention. To summarize the findings of the work, this is the first paper or the first work to try to understand how EasyList affects the web in a broad, longitudinal way. As popular as EasyList is, it's maintained by just 5 people, which is pretty surprising given the popularity and importance of the project. We find that over 90% of EasyList provides little to no benefit in common browsing scenarios. We also are able to provide a quantified taxonomy of how advertisers and trackers evade filter lists. And then last, we're able to build on these findings to improve how content blocking is done on mobile devices. And with that, I'm very grateful for your time, and thank you very much.